Yes, ma'am.
Okay, fine. Shall we start?
Yes, ma'am, please.
So, how many students are there?
Uh, Ma'am, around 30 people are here.
Okay. Okay. Yeah. Good afternoon to everyone.
True, ma'am. You can start, please.
Okay. So, yes, thought of covering some characterization of functional materials. Um, Hope you might have had other manufacturing techniques and other topics in rest of the sessions. Okay, so characterization is very important one. So it's help to whatever the process you are carrying out. Okay, so to ensure that how the process happened, with the suitability of the material or product for the final application, it is required some study. Okay, so that study can be done through the characterization processes. Right? So yeah, just to let me give what are the materials. So materials can be classified generally into three types. One is metal. Okay. So one is metal, another one is polymer, third one is ceramics. These are the categories. Any materials can be grouped under the major three classifications. There are another category that is called composite. Composite is nothing but combination of any of these uh, two among these three. Okay, so you can find any material for the application. Either it can be a metallic material or polymer material or ceramic material, and you might have seen some composite also. Okay, so the materials can be classified under these major title. So, why material characterization is needed? Of the service of the component, whether the component is fit for the service or fit for a certain application, whatever you are aiming for, that can be connected by correlating the structure with the properties. So, the structure and properties can be studied by the characterization. So, material characterization techniques are generally classified into two major types. One is a destructive analysis, another one is non-destructive analysis. It is fine, right? My voice is audible.
Yes, ma'am, you're audible. This is fine. Reading source, ma'am. Please continue.
Okay, you can able to follow. Okay. Yeah, so there are two major types. One is destructive analysis, another one is non-destructive analysis. As mentioned by the technique, non-destructive analysis means you need not to cut and do any preparation the sample for the analysis. So destructive, again under destructive analysis, there are two major category. One is microstructure analysis, second one is mechanical testing. So we'll see one by one. So first we'll discuss the destructive analysis, then we'll move to the non-destructive analysis. So as I mentioned, destructive analysis, one is used for microstructure studies, another one is for uh, measuring the properties through mechanical testing. So microstructural studies can be done by using certain microscopes with the help of certain microscopes. Okay, and the XRD techniques. There are many other techniques. These are the major techniques commonly used for study the basic structure of the material. Other than these techniques, there are multiple other techniques for a specific purpose. Analyzing the specific properties, it can be used. Okay. So first one is optical microscope. Yeah. Before getting into the technique, so irrespective of any process, it is required a defined sample preparation procedure. So you must do a standard procedure for the sample preparation. The standard procedure involving the standard procedure, it is mentioned sorry, there is a standard ASTM standard you can follow. the standard procedure for the preparation. You must follow the standard procedure to get the better result. Okay, so you might have come across all these processes during, if you have done any of the microstructure analysis in your college or during your degree program time. So, how to start the sample preparation? If you have a bulk sample, it is required a cutting process to make a small sample, because every equipment, whatever I have mentioned, each microscope has its own limitation of sample size. So for that, what you have to do, if huge samples you are having, so it should be cut into a smaller size which can fit into the machine. If it is too fine samples, which is very difficult to holding during the preparation, that can be mounted with the help of some resins. These resins basically hold the samples, then the whole mold you can use for the sample preparation. Okay, so it is not restricted only to the fine sample, even bulk sample, which can fit within the size of the mold, you can mount and then go for the sample preparation. Okay, so once it is mounted, it's supposed to be polished well by using through multiple steps by using the emery sheets. Emery sheets, it is available readily, but how it is prepared? Generally, silica carbide or alumina particles, the ceramic hard particles, will be embedded in the sheet by using resin. So those particles are hard enough because those are ceramics. Um, so those samples will be having a higher hardness. When you are rubbing your material against that hard ceramic particles, your samples will be removed from the surface. Okay. So this is one of the emery sheet. It is stuck over the wheel. This is a wheel. This is a polishing machine. So this is the emery sheet. So this is the mold mounted, a small sample mounted using a polymer resin. So when you are keeping the sample against the rotating wheel or stable wheel, if you give the movement manually by rubbing action, so your material will be removed gradually from the surface. So what you have to do, from the coarser size to finer size, you have to change multiple papers. Okay, by that you are reducing the scratches. Whatever you are introducing during your polishing will be fined down. Okay, so finally you should come up with the mirror image. Why it is required? If there are any scratches or any cutting marks are there during analysis, that will hide whatever the features are available on the surface. Okay, so the mirror finishing is very must for microstructural analysis. So once you have done the sample preparation, then the sample is ready for taking the microstructure. Yeah. In case before taking the sample to the microscope, there is a intermediate step that is called etching process. Etching process is nothing but you allow the sample to react with the chemical for a few seconds. So the chemicals will be reacting on the surface of the sample at the contact region at a selective rate. Okay. So those, each sample has its specific chemicals which can react with the sample without disturbing other feature. Only it can react the selective features. Okay, so those chemicals, the suitable chemicals for a certain samples are known as etchant. The chemical reaction what we are allowing the sample to react with the etchant is called the etching process, right? So every etching process required a certain time. Beyond the time, the chemical will react more than the required time or optimum time. Then the reaction will be happening throughout the sample. Then your features will be hidden by that. That will end up with some corrosion product that during the reaction between the chemical and the sample. So you have to be careful with the time of exposure of the chemical with the sample surface. Okay, so that is called etching time. So you have to be careful with the etching time, how much you are exposing the sample with the chemical to avoid the hidden or losing the features what you are aiming to look into the microscope. Okay. So the etching process can be done in a two-way. One is manual etching, another one is electrolytic etching. In manual etching, directly you can take your chemical, just you can dip the sample into the etchant, you can allow it for some time, you can take it out, you can dry the sample, and you can look for the features. Or instead of dipping the entire sample into the solution, you can keep the sample outside, dip the chemical by using cotton, and that cotton can be uh, touch over the surface. So swabbing, that action is called swabbing. So by that rate of reaction you can control. Okay. So apart from manual etching, there is a electrolytic etching where you can pass the current for enable the reaction in a better way. Some samples naturally which is having the high corrosion resistance may be difficult to do with the manual etching because already it is high corrosion resistance. So the chemical, if you allow to react manually, it won't react. The reaction will not be feasible, or it won't be severe. So we need a little severe reaction for etching the select features selectively. Okay, so that can be done by using the electric current. So that process is called electrolytic etching process. Your etchant will be used as a electrolyte. Then your sample will be kept as anode and suitable cathode will be there. So you can pass the current, then selective etching will happen. Example for electrolytic etching is stainless steel samples are high corrosion resistance. Someone is speaking in between. So, Prachi,
Um, yes,
what is
ma'am.
that disturbance in between? Any question or what is that?
Does anybody have a doubt so far? Ma'am, can you take up and then we continue with the lecture? Yes, ma'am. So far nobody is speaking. Maybe there is a technical glitch. Uh, could you please-
Okay, so I'm getting some noise in between. So I thought if you have any questions. Okay, shall I continue?
Yes, ma'am. Please continue.
Okay. Yeah.
Yeah.
So manual etching, there won't be any current usage of current for enabling the corrosion, the reaction rate to enhance the reaction rate. But electrolytic etching, so okay. So stainless steel, nickel, this material may require the electrolytic etching, which is having high corrosion resistance, may be difficult to react with the chemicals. So the basic microstructure analysis equipment is optical microscope. So optical microscope can give major details. Most of the details can be obtained or derived from obtained by this. Okay. So whatever the standard sample preparation procedure I mentioned, that is required for doing or taking microstructure by using your optical by using the optical microscope. Okay. So optical microscope basically will give you some microstructure. Nowadays microscopes are coming with the attachment, it is called image analyzer. Okay, so image analyzer, it has a software, inbuilt software, image j software it is. So image j software can help you to measure some features present on the samples. Okay, so before going into the microstructure analysis, just I want to mention one thing here. If you want to see the grain boundary, then only it is required the etching process. If you want to see any secondary phase particles or precipitates, in case of steel, some inclusions will be there. So those kind of features in as polished condition itself, you can see. You can able to see under microscope. So those processes does not require the etching process. Okay, so etching process basically it is required to reveal the grain boundaries. Other than that, whatever the hard phases are present in the sample or any defects are present like a porosity In case of welding samples, shrinkage cavities. So those defects can be analyzed even without etching process. Okay, so etching process you can skip if you are interested in seeing some other details. Only if you are interested to see the grind boundaries, then you have to choose the etching process. Otherwise, you can skip this step. Okay. So through optical microscope, you can get major details of the material. This is one of the image taken at the weld interface. This is the stainless steel to inconel alloy weld by using the inconel filler material. So you can see the macro view. So the beauty of the optical microscope is you can cover the large area of the sample. So yeah, that is the major benefit of the optical microscope. So whatever the analysis you want to carry, first you have to take a optical micrographs. Then you can get the feeling of the overall structure present in the material. Then you can go for the particular location for yeah, wherever you are interested to look into. So yeah, you can start your analysis by optical microscope. You can see the scale. This is 1 mm. The total length is about some 20 mm length we could able to cover. The sample thickness is 12 mm thick. So such a huge area and details in the huge area could be collected by the optical micrographs. Obviously this is a montage image call. So in a single go or single click we could not able to cover the entire area. So multiple small images we have taken. What is the maximum possible size, then we stitched all the images in the proper sequence, so we could able to get the detail. Okay, so this is one of the weld sample. We were looking for how the interface at the joint, and looking for any presence of defects. Those analysis can be done by preparing the cross section of the weld. So again, optical microscope, as I said, from the macro graph, the region of interest, this is weldment to the base metal one side, this is weldment to the base metal of other side. Okay, so these details, if you want to see little higher magnification, you can magnify and take the images, and you can look into the details for this. So this is after sample preparation, final polishing plus etching process, we could able to see the grinds. So you can see the combination of finer grinds and coarser grinds. Coarser grinds you can find in the heat affected zone. Okay, so this is another image taken from the functionally graded aluminum Al3 nickel gradient directional solidification cast alloy product. Okay, you can see the that intermetallics morphology variation from bottom to top due to the directional solidification. So the gradient structure could be able to capture by the optical microscope. Okay, so as I mentioned, large area if you want to cover, small portions, the continue image you have to take, then you can stitch the image, that is called montage image, that will give the overall structure variation in a particular the selected area. This is optical micrograph of additive manufactured sample. You can see the individual pool, how it got deposited during the printing process. Okay, so in all direction, one is x minus direction, y minus direction, and the same printing done by alternating means x y like that. This is in rotational, like rotating the axis and printed. So all these actions, how it affects the internal structure of the 3D printed component, it has been studied by using optical microscope. Okay, so yeah, this is little higher magnification at the interface, how the joint is. This is also again the 3D printing component in Cornell 718. Okay, so at the interface, whether the joint is good or any defect is there, so you can magnify little and you can see, um, look for the defects and how the structure is present in the sample. Okay, so the another tool is SEM. You might have heard that. So optical microscope. The major limitation of optical microscope is the magnification. You can magnify up to 2000 any of the samples. Okay, so beyond any details, if you want to look into, you need a some different equipment. So yes, SEM fulfill that need to look the features at a higher magnification. Okay, so higher magnification means SEM can magnify the samples up to 5 lakhs also. Okay, so standard SEMs are available which can magnify up to 2 lakhs without compromising any resolution. This is the SEM microscope available at IIT Dharwad, which has a FET source. So SEM generally comes with two different sources. One is FET source, another one is a tungsten electrode. Okay, so compared to tungsten, FET will give field emission ion gun will give the better resolution. So this is the SEM image of spider. So SEM can provide the details, morphology, topographical images of anything. Okay, so as I mentioned, whatever the sample preparation procedure is required for taking the optical images, same thing can be done for SEM also for looking the grain boundaries or other details. Otherwise, it does not require any sample preparation. Only thing, you should prepare the samples free from any dust, water, like that. Whatever the contamination, it will create the contamination to the gun or any particles which disturb the electron flow. So you know that SEM is working with the principle of electrons, source of electrons make fall on the sample surface. So whatever the diffraction or scattered electron beams are coming out, that will be collected and converted into the images. So whatever will disturb that electron path, those things to be avoided. Okay, so other side, including the sample preparation, if directly you are placing the sample which is not conductive, non-conductive samples to be coated with the conductive particles, generally people will go for gold coating or platinum coating. Okay, for enabling the conductive nature of the sample. Okay, so otherwise you can take any feature as it is without any sample preparation. If it is a metallic sample, you need not to, you can skip even the coating process. Okay, so this is one of the image, that is a spider image. By using SEM, it has been clicked. So yeah, as I mentioned, this is a metallic sample after fracture to look into the fractography of the nature. It may not require any sample preparation, polishing, other thing. If it is a metallic material, it does not require even coating process. As it is, you can load the sample into the SEM machine. You can try to see the feature, how it got fractured. This is one of the fiber reinforced composite. Okay, so you can see the fiber, it's not affected during the fractured process, but here the fracture propagation you can see along the fiber. Okay, so these are the informations you can get by using SEM. Yeah, if you have developed a composite like alumina embedded the metallic matrix or kind of thing, so how the particles distribution, the newly added thing also can be studied by using SEM. Yeah. This is precipitates present in stainless steel sample, which I showed the macrograph in optical session. Um, Okay, so from those wells, we have taken the sample, prepared, following all the procedure, ASTM standard sample preparation procedure, whatever I mentioned in the first slide, like cutting, polishing, everything. Uh, Without etching, we could able to see the precipitates present in the weld zone of those. Okay, so based on the precipitates density nature, you can see either bright or dark, some gray color appearance. Okay, so this will give another information. So I'm not getting into all. Just to hear the messages, you can see the precipitates or any features even unetched condition, means as polished condition, and using SEM machine. Okay. Yeah, this is the fiber reinforced matrix. Okay, SEM can be used for doing some measurement also. So there will be a scale will be available based on the scale at what magnification you are looking the picture. Okay, so you can measure, do the measurement also. Here they have measured the fiber size. So same way, if some coated samples are there or any printed sample, in case that 3D printing, individual pool size you want to measure. So those details, or in case of precipitates, you want to measure the precipitate length or size. So everything can be measured, so that option is available in SEM. Same thing is available even in optical, but only thing, feature, very fine feature cannot be in macro level. Whatever in the measurable level is available in the sample, those can be measured using the image analyzer software, whatever is attached with the optical microscope. Even optical will provide the same facility, same purpose. Only thing, for fine details you cannot do using optical. For that you can go for SEM. Okay, so SEM generally it will come with the two detectors, secondary electron detector and backscatter electron detector. So general fractography, these things you can take using the secondary electron uh, detector. Okay, so that option you can pick and you can take. In case there are precipitates, you have to go for a backscattered electron mode. Okay, so where there is a difference of the phases or features, uh, which is having a density differences, those can be clearly distinguished when you're picking a second backscattered electron detector option. Okay, so just a feature you are looking for, you can go for a secondary electron mode. So either secondary electron mode or backscatter electron mode, these two will serve the purpose of taking the images. Okay, so in addition to these two detectors, there are another detector. It is a EDS detector. People used to call as EDAX detector also. The EDAX detector serve the purpose of measuring the chemical composition. So the regular SEM will come with the SE BSC detector inbuilt, but EDS detector is not inbuilt. You have to buy additionally and attach with the machine. Okay, so these detectors can help to measure the composition of any feature or over area, whatever you want. So you have to select the area. You have to go to the EDS mode, select the region and click on that. You will get the composition from the respective region. This is one of the interdendritic region of cast product. You can see the features, different features are present here. So individual features are having a different composition. So how the variation in this, I can spot all the places, spot my cursor here and try to find out the composition from these areas or spots. Okay, so that facility also can be provided by the SEM. So this is one of the coating sample. Again, you can see the color contrast differences based on the composition variation within the coating material. So if you want to analyze some phases enriched with the some component, some phases are depleted with the some component. This is base metal, this is coating over the substrate. So all these things can be measured by using the SEM EDS analysis. I can pick the region, I can spot my cursor here. So electron will fall on this region, then spectrum will come out from that particular region. The spectrum will be run with the database which is matching with the standard elements. It will give you the what elements it is present in that particular zone. Those can be analyzed by using the SEM. So either you can go for a spot selection, or if you want to see here the faces are very clear, you can pick some region and identify what it is. But in case these kind of um, coating or some compound is formed on the surface. This is the surface, sorry, substrate. This is the some product. Okay, vertically it has kept. But if you can see, there is no smooth variation. There is a zigzag pattern is present. In that case, the spot analysis may not help you to identify the composition. What you have to do, you can go for a line scanning. So line scan, you can select the line from where to start, where to end, and you can select the particular element also. I am interested how, in this particular case, how titanium is distributed across the line. Okay, so this is the pattern of titanium across this product, whatever formed over the substrate surface. Okay, so if it is identified some compound, how iron is distributed, how aluminum is distributed, like that individual elements you can pick, and the distribution map you can get out of it. Okay, so that facility also will be provided by SEM EDS detector. This is one of the steel sample. So done the corrosion testing. So end of the test, we found some corrosion product on the surface. Okay, so this is also could be found by SEM. This is as polished condition, right? So after polishing, we could able to see the layer formed. This is a steel sample, ferrous sample. The product is iron oxide. Okay, so for identifying some features, if any additional features, anything is present at the end of any test, any stage, you can do the analysis to find out, or to look into whatever the changes happen inside the sample, that can be understood by that. Okay. So, as I mentioned about the EDS detector, same way, a separate detector is available which can come with the SEM. So, you have to buy additionally and attach to the SEM machine. Okay, so that detector is EBST detector. So, it again, this detector serves a different purposes. So this is your pole. This is the inside chamber of SEM. So this is the pole piece from where top of this your electron source will be there. So from the source the electron will come. It will fall here. Generally secondary electron detectors will come as an attachment with this. Okay. So uh, BSc detector also will come either from back or top of this only it will come depending upon the make. Okay, this is EDS detector, this is a EBST detector, this is the sample stage. Generally the sample stage will be parallel or straight line with the pole piece. Okay, so it will come down, so you will place the sample here, electron will form straight on the over the surface. So the reflected or diffracted scattered electrons will be received by the detector and we will get the image. In a particular case, that means EBST. So EBST case, you have to tilt this stage to the 70-degree. So this is the 70-degree from its original position. It will be down here. So that will be rotated at 70-degree. Praveen, your phone at the clock. So it will be rotated to 70-degree. So the samples to be 70-degree. Electron will fall on the sample. That whatever the diffracted rays are coming out, that will be collected by the Passport screen. Then the process will be done internally. Okay, we will get some data from this. Uh, Unlike EDS or SC, BSC images, these images directly you can see on the screen, right? So these results also, when you are using EDS detector, you will get in terms of number or in terms of spectrum you will get. In case of EBST, you will get a data, the diffraction data, theta values from the machine. You have to use a separate software for the analysis. So BSE image, SE image, EDS does not require a additional software for the analysis. but EBST requires. So by using the additional software, you can get lot of informations. So the basic informations, yeah. So the basic informations, what are the informations you can get by using the EBST detector is grain size. So grain size, same thing you can get from optical also, right? But if too finer grain size, that is difficult to capture by optical microscope, so then you have to go for EBST analysis. Then grain orientation. What is the grain orientation? Orientation of one grain with respect to the another grain. So that can be studied by using the EBST method. Grain size distribution. It can be coarser, finer, elongated. So the size of distribution map also you will get by using the EBST thing. And texture. The orientation of grains with respect to a particular direction. For example, you have a rolling plate. Okay, so along the rolling direction, what is the distribution of, there are background more information about the grains. Any material composed of atoms has its own orientation or arrangements in the space lattice. Those arrangements uh, can be studied or understand by the unit cells. So unit cells will have a, or representing a particular standard shapes, like a hexagonal, cubic. Okay, so those shapes are called as crystal structure. Any material will have its own crystal structure. So one crystal structure will have a own slip planes. Slip planes are nothing but a plane readily available or readily undergo for deformation when any samples experiencing the load. Okay, so when you are having the component for any shape, for making any components products, you must know what are the slip planes, slip direction, orientation of the grains, to understand whether further deformation the material can face, or it may fail if I am applying extra load. So those things are required, the texture analysis. So people who is mostly working on forming operations, rolling operations, sheet making, okay, so product, thin product making, they are particular about the texture of a texture present in the component. Okay, so that information you can get from the EBST analysis. Then EBST also provide you the detail of presence of strain inside the material. So a cam map will give you the understanding of the stress distribution or strain inside the material. Okay. So another tool, so whatever we have discussed, those things, multiple detectors associate with the SEM machine. So machine is same, single machine, multiple detectors will be used. Majorly it covers microstructural analysis, grain size, distribution, particles, any precipitates, composition measurement of those phases, precipitates, etc. Same way, separate equipment is available, that is TEM microscope. So that is again serve the purpose of getting the microstructural details little higher magnification than SEM. Okay, so how SEM is following a standard sample preparation procedure. Same way, TM also has a standard sample preparation procedure, but it is not as simple as the sample preparation of uh, s- any specimens for SEM analysis. TEM require a very thin sample, around some 30-40 microns. Okay, so preparing a very thin sample in a regular manner, it's impossible. Okay, so it is a transmission electron microscope. In SEM, whatever the electron beams falling on the surface, it will scatter or diffracted. Those diffracted beams will give you the information. In case of TEM, whatever the beams are transmitted through the samples, that will be collected from other side. From that, we will extract some details of the samples. Okay, So the sample means the sample should be enabled to transmit the incident electron beam to other side to get a better result. So the transmission will happen when the sample thickness is as minimum as possible. The maximum thickness is allowed is 40 microns. It can be lesser than that also. Such a fine sample preparation is impossible in a regular manner. It is followed a typical procedure. There is a FIB, focused ion beam. The ion milling procedure is there. So ion milling, by using the ion, you can do the milling the surface of the sample. From that you can extract the very thin filament, lamella it is called. So for the analysis, that is one way, but it is very costly because you are using ion beams for milling out or cutting out the sample from the bulk material. So the cost wise, cost effective method is generally people will do how we are using the emery sheets for preparing the SEM samples. Same emery sheets can be used, but it should not be in the molded condition. Okay, the sample should be out from the mold or unmounted condition. Use the emery sheet, polish, thin down to whatever the maximum size you can reach out, either 80 microns or 70 microns. You can thin down the sample. Then you have to cut a small disc. The standard size is 3 disc will be extract from the thin down sheet. Okay, from the bulk you have to slice the sample. From the slice you have to thin down to 70 or 60 microns. From the thin down sample to 3 disc you will cut. So now a 3 disc of 70 or 60 thick micron size samples will be available in your hand. Now what you have to do, that sample to be placed in pips, a machine called pips. The pips machine will allow to fall the ion beam from both the sides at an angle. Okay, so when ion beams falling from both the sides, it will thin down the sample. One point it will generate a hole at the interface. So once it is generate the hole, close to the hole, the sample size will be as thin as possible, which can transmit the electron beam. Okay, so now the sample is ready for the TEM analysis. You have to load the sample inside the chamber, then turn on the electron beam. So electron beam will fall on the sample. It will be collected from other side. So you can get the details, whatever the analysis or whatever the features you are looking for, you can get the details from that. Okay, so these are the small particles embedded on some of the matrix. Okay, so these particles could able to revealed by the TEM. Okay. So this is one of the sample, whatever I showed the macro image and the SEM that precipitates. Those precipitates are larger. In some condition during the creep, the same sample, it formed a very fine grain. So you can see it is a nanometer, 20 nanometer is the scale size. So such a small precipitates, this is the dislocation. During the creep test, when you are applying load, excuse me, dislocation generated, dislocation is moving. So these dislocations got pinned by these precipitates. Generally, the addition of alloying element in any material is to strengthen the material. The strengthening is coming from the pinning of dislocations by the precipitates, right? So these are evident by using TEM. Okay, so in this sample, we could able to very fine precipitates in the sample by doing some heat treatment. Then we did tensile testing also, as creep test also. Okay, so at the time of failure, we were trying to understand how the pinning is happening. So the sample is prepared from the bulk, whatever the procedure I mentioned, 3 disc prepared. Then we could able to analyze how these precipitates and dislocations are present in the sample after certain testing conditions. Okay, so these are the dislocations. These also dislocations it is going. So based on the precipitate size, there are multiple mechanisms not multiple, two major mechanisms. One is the dislocation overloop or once bypass or cut through mechanism. So precipitate size will decide whether it will be a cut through mechanism or once loop. If precipitates are larger, your dislocations will make a loop over it, then it will try to pass it. If it is a small, it is easy to cut through and pass the precipitates. Means whenever it is resisting the dislocation move other side, it requires more load to push the dislocation to other side. Means your system is resisting for the further deformation. Means your material is too strong. Strength means what? Resistance to deformation. Resistance to deformation means what? Internally, your dislocations movement will be arrested or it will be restricted by that. Okay, so these precipitates will act as obstacles. So, Prachi, do we have time? Prachi?
Hello. Good evening, ma'am.
Yeah, good evening, Prachi. We have time, right? Shall I
Yeah.
continue or?
Yes, ma'am. We have 15 minutes.
Okay, I'll try to finish by that. Okay.
Yes, ma'am.
So the yeah, another advanced characterization technique is XRD. So XRD techniques will help you to find out what is the crystal structure. As I mentioned, any material it is composed by the presence of atoms. Atoms will have its own presence orientations. So that will be understand by certain basic shapes. Those are called crystal structure. So if any new material are there, you don't know the crystal structure. If you want to find out the crystal structure, XRD is the suitable method. So in XRD, sample preparation, either you can keep in the form of powder or bulk sample, but it does not require any polishing like a mirror image, whatever we were trying to get for SEM or optical micrograph. But yes, a little bit surface finishing it is required. Some smooth finishing you can finish for having some details from the surface of interest. You have to do some minimum preparation and load the sample here. So x-ray will fall, then diffraction pattern will be, sorry, diffracted rays will be collected here. So those diffraction details, again theta values will be available. The machine will give only theta values with the intensity. Then you should have the software for analyze the data. Okay, as like EBSD, XRD requires a separate software for analyzing the data. Machine only will give the theta values, two theta values. I think everyone must aware XRD works with the principle of Bragg's law. So you know Bragg's law, n lambda equal to 2d sine theta. So incident beams, whatever is fulfilling Bragg's law, those will diffract the beams. These diffracted beams will be collected by the machine. So from that theta value will be given. So theta is directly related with the intensity of the elements. So that will help to find out the what metal it is, what material it is. Then D is the lattice spacing, space between the plane. So D is again related with the A, lattice parameter. So whatever the unknown parameters, if you find out, you can crack what is the crystal structure of the particular sample. Okay. So with those data, you can identify what phase it is. Like here, the phase is ferrite, purelite, martensite. Okay, so like that, whatever the unknown phases are present, that can be identified. So it can give the grain size also, as like SEM and TEM optical microscope. But there you will get the image. Here you will get the number. So again, this also will give the texture like EBST, but here you will get the bulk texture because the area covered by the X-ray will be larger. So you will get the bulk texture by using XRD. Texture, whatever you are getting from EBST, that will be local because the area covered by the electron is smaller. So local texture will be given by EBST, bulk texture will be given by the XRD. And any thin films are there on the top. Some substrate is there coated with the thin film. That thin film composition, or you want to understand the phase, again follow the same procedure. You can find out the composition of the thin film also. Okay, so any archaeological samples, unknown samples you are finding, you want to understand what could be the crystal structure, all the details, that can be done by using XRD. In addition to all, in addition to all, stress measurement also can be done by using XRD machine. Yeah. So as I mentioned, all those methods coming under the microstructure analysis, part of the destructive analysis. Another testing method is a mechanical testing where you can measure the mechanical properties of the component. Okay, this is also a destructive testing because end of the test you are spoiling, you are damaging the sample. So mechanical testing, you may aware of tensile test, harness test, fatigue, and additional these are the special tests for a particular application, right? So tensile test and harness test, everyone must have done in your lab for any samples if you're working on, right? So you have to prepare the standard sample, load the sample in the machine, okay, apply the load, so you will get the stress strain curve. So by using stress strain curve, you can get the information of strength, ductility, toughness, all the basic mechanical properties can be uh, get can be analyzed or measured by using the tensile test. So in tensile test, one thing you must remember, the orientation of the sample preparation with respect to the sample. For example, this is a rolled plate, so in which direction you are preparing the sample, that will give a different stress strain curve. It is a comparable variation you can observe with respect to the orientation of, at which you are preparing your sample. Same thing is applicable for 3D printing samples also, in which direction you are picking for your sample preparation. Again, it will affect your final result. So you have to be very careful the direction or orientation what you are choosing for the sample preparation. So the next basic mechanical testing method is a harness method. There are multiple harness methods based on the load applying and the area covered and whatever the indenter you are using. So you can classify into multiple types. Okay, so the larger area will be covered by Brinell harness sample. It is suitable for the measuring harness of any cast product because cast product will have a heterogeneity in its microstructure distribution. So Brinell is one of the suitable method for that. If cast is very sample is very thin and it is very brittle nature, then it is not suitable. You have to move to other methods because Brinell test you will apply about 1 kg to 10 kg load you will apply. Okay, so Rockwell you can apply up to 3 kg loads. Okay, Vickers again up to 1 kg, micro Vickers again up to zero point 0.1 microns. There are another method, nano Vickers, where nano indentation, where you will apply even lesser load. So very small features if you want to measure, you have to control the size of the indentation, means you have to focus only on that. So then you have to go for a finer one, either micro Vickers or nano Vickers, right? So less load will control the uh, um, size of the indentation. So your harness value will be measured by the load by the area of the indentation. So for accuracy, whatever the features are present, you have to go for the analysis uh, under microscope. Optical micro would be sufficient. See the feature, fix or see the details, then you fix or pick the suitable harness method for measuring the harness. So these are the typical machines you might have seen. Okay, this is Brinell, Rockwell, and the Vickers machine. So you can see when you are doing harness test, there will be indentation. This is a typical indentation by a wicker, micro wicker harness, right? So load divided by the area of the indentation will give you the harness value. Area will be calculated by the diagonal length. There is a standard formula. Formula I have not included here. So by using that, you can calculate the area. So by using the area, load by area will give you the harness number. Harness generally will be given in the unit of number. So move to the non-destructive testing. If you made the product, but you don't want to disturb or destroy the sample, but you want to measure some details from the component, then you can go for the non-destructive testing methods. For example, huge pipes are there for oil refineries or any gas transportation. Those pipes, some leakage is there. Every time you cannot go and cut and see the sample pipes. As it is, you want to do the analysis, any cracks are present, any defects are present. So in that case, non-destructive testing is a suitable method. So non-destructive testing generally provide any defects are present in the component. You need not to destroy the sample. As it is, as a complete component, you can take it for the analysis. You can load the sample, or machines will be portable. On the spot you can take the machine, the area where you want to do the analysis, you can focus on that, you can get the information. So visual inspection, directly you can look into the samples, just whatever for your naked eye, identifying the defects or cracks, that can be done by the visual inspection. Liquid dye penetration, by using some liquids, you can identify the cracks or defects present on the sample. Magnetic particle inspection, only magnetic material can be detected in this way. You can pass the magnetic field where there is a defect, there will be a magnetic flux leakage will be there, you can identify the defects. Eddy current, again by using the current, if there is a defect, there will be a leakage by current, you can identify the location. Ultrasonic waves, you can pass the waves. If there is no defect, the one side there will be a transmitter, other side receiver will be there. So how the receiver receive the signals, based on that the presence or orientation of the defects can be understood. Radiography, again similar to ultrasonic, you will apply the X-ray or gamma rays for analyzing. So pass the X-rays or gamma rays you will pass, you will receive the signal like X-ray. You will develop the X-ray. You can get the scanning of that. You can get the information out of it. Leakage test. If a pipe is there, you cannot able to locate by any of these things. What you can do, pass the water or any liquid or gas up at higher pressure. If there is any hole is there which cannot be picked by this, there will be a leak. So pressure leak test, that is also one of the way to identify the defects present in that. So this is a typical standard procedure of dye penetration test. What you have to do, you have to this is a component, you have to apply a dye over it, clean it. There is a developer, you have to apply on over it. So if there is a defect, dye will penetrate through the defect. When you apply the developer absorb the dye from the hole. So from that you can understand there is a defect. The presence of defect can be understood by that. Dye will penetrate into the defect if there is a opening, surface opening, okay, by capillary action. So allow it for some time, then clean the surface entirely. But whatever the dye absorbed inside, that will be sitting inside. If you apply some absorber here, so the dye will be absorbed by the developer. So then you can identify or locate the presence of cracks. So this method only analyze the surface defects. So as I mentioned, magnetic particles, for magnetic material it is useful. It can be applied for surface, identify the surface defects, as well as the any defects present inside the material also. So if there is a crack, there will be a flux variation in the flux. Okay, so with the leakage, you can identify the presence of the defects. But it is suitable only for the magnetic material, especially for steel. Steel industries uh, majorly use this technique for identifying the defects. Radiography, this is the portable radiography machine. This is a huge pipe. So there is some leakage or they have welded here. So just to check the weld quality, whether any defect is there. So people trying to one side transmitter will be there, other side receiver will be there. So they will keep and receiver will give the signal. If there is a presence of defect in the one when you are developing the scan, you can find the absence of x-ray in that place, so that will help you to identify or locate the presence of defect. Okay, I'll stop here, so we'll move to the question session.
Yes, thank you for the session. Floor is now open for questions. Anyone has any doubt? Anything regarding the slides that were presented? If you have any doubt, please raise hand. Yes.
Good evening, ma'am. It's Prashant here.
Yeah, good evening. Yeah, hello Krishna, please tell me.
Ma'am, as you were presenting the EBSD slide, you mentioned something about the KAF. Like,
Your voice is not audible. Can someone
Yes, ma'am.
yeah, now I'm audible, ma'am.
yeah, now you're audible. Yeah, please tell me.
Yes, ma'am. So in the EBSD slide, you mentioned about the KAF and how we can measure the stress or how we can get an idea of the stress in the microstructure.
Mm.
Ma'am, can you please elaborate on that? How what is that? How do we
I
like
lost your
bring that?
voice again. You okay? Stress, actually you won't get the magnitude, but the stress distribution you can see from the image. The distribution of the stress, you won't get the quantified value. Yeah, so this is one of the image. Okay, so see, within a grain, it's supposed to have a uniform color here, right? So you can see the gradient in the same color. So here you see the gradient within a grain. So you can see the gradient within a grain, right? So it indicates that there is a presence of stress. You won't get the quantification with this, but you can get the qualitative analysis, the presence of stress in this.
Yes. Okay, ma'am. Okay. Thank you, ma'am.
Hello, ma'am. I
Yeah,
have a yeah. I am having one
yeah.
question. Yeah, how is the how are the how is the material characterization different for composites? Hello.
Composites also remain same. Only thing, what composite you are using, again you have to take care that sample preparation and analysis. You have to select your, see, there are multiple a number of characterization techniques are available. If it is a metal matrix, a composite also has a multiple types. If it is a metal matrix, same analysis you can apply. If it is a polymer matrix, polymer is non-conductive, right? Again, whatever I showed, that fiber reinforced, so as it is you can go for. It does not require any etching or anything. So only sample preparation will vary sample to sample, based on your type of samples, specimens.
Any other doubt? Okay, ma'am. So we can now close the session. The doubts are done.
Okay. Yeah. Thank you. Thank you.
Thank you, ma'am.